Hi everyone, welcome to this seminar on mean field games and machine learning. So today it's a great pleasure to have Kai Cui from University TU Darmstadt, who is going to talk about learning mean field games and two papers and two ideas, entropy regularization and dense graph limits. So yes, thank you very much for accepting the invitation. If you want to start, the floor is yours.
All right, thank you for the nice introduction and also invitation. So my name is Kai Cui, and yeah, it's a great pleasure to be here today. Today, I would like to present to you our recent works on applying entropy regularization to mean field games, and in particular also learning in mean field games in order to achieve convergent algorithms that converge to approximate solutions for mean field games. And in the second half of this talk, I would also like to briefly touch upon our recent extension of the discrete time mean field games to dense graphs using the dense graph limit theory of graphons. So the following presentation will be based upon the following two works, and they are available online. Now, let us begin firstly with a short motivation. So in real life, it happens that we encounter a variety of many agent scenarios, such as, for example, here you can see a routing problem of perhaps automated cars, where many cars essentially have to plan selfish or socially optimal routes to get from their current location to their destination location. Or perhaps you could also consider many people in a vaccination game where they can either selfishly or socially optimally choose to vaccinate or not under a given model. And there are many other such scenarios. And essentially in most of these scenarios, what we have is a kind of weak interaction where one agent's actions have a very negligible influence on the many other agents in the system. And in these scenarios, what we often try to ask ourselves is how do we analyze the optimal sequential behavior of such agents in the aforementioned systems? And one very empirically effective method that has been used in the recent years is multi-agent reinforcement learning, which can handle such multi-agent systems. However, still, those conventional methods in multi-agent reinforcement learning can be inadequate for a variety of reasons. So in particular, there are these 3 points that I want to point out here. For one, there could be computational intractabilities that essentially stem from the curse of dimensionality, since we have essentially an exponential complexity of the state space in the number of agents. And for two, and closely related to the first point, therefore, in the cooperative case, where we just have essentially one objective for all the agents that they are trying to jointly optimize, under this assumption of weak interaction, we will also have a very weak learning signal, since essentially, if we want to try to learn the optimal actions of one single agent, then it is hard to discern if the action was good or bad, because there were at the same time also lots of other agents that also take actions. And thirdly and finally, there is also the well-known issue of the complexity of computing Nash equilibria in the competitive case. And so what we can use to solve this problem is to use mean field models. And I assume many people here probably already know about them. So mean field models are essentially large, weakly interacting particle systems where we have this so-called property of propagation of chaos, where this essentially means that if we look at any pair of agents, then the pair of agents is essentially stochastically independent of each other over time, as long as the system is large enough. And so to formulate such a mean field model, we start out in the finite n agent setting in discrete time. And we simply give each of the agents I a state, a random state variable xti from here really a finite state space x. So really we want to look at the simplest case that is possible for mean field games. And this random state then simply evolves by sampling the next state from some distribution that depends continuously on the previous state, the action that was taken by the agent, as well as the empirical distribution over agent states. And so, similarly to the state, we assume that the action variables, the control variables, are from a finite action space and simply given by a local feedback policy. So if we have a certain state of the agent, then this policy simply gives us a distribution over actions it will take. And therefore, we obtain the system that we see here below. Now, all that is really missing is to also define an objective. And again, since we are trying to look at the simplest case possible, what we will do is we will give each of the agents a finite horizon objective. So what each agent is trying to optimize is the expected sum of rewards over all time steps, where the reward is given by a function simply of its own state, its taken action, as well as, again, the empirical distribution over agent states. Now that we have this objective function, we can define the typical solution concept that is quite commonly considered in multi-agent settings, namely the Nash Equilibria. So an approximate epsilon Nash equilibrium is essentially defined for some suboptimality epsilon that is non-negative as a tuple of policies, one policy for each agent, such that no agent can improve its own objective by more than epsilon by choosing another policy for itself, by single-handedly deviating from this tuple of policies. And this essentially leads us to a kind of high-level meta game where agents can essentially statically pick a local feedback policy, which is really just a decentralized, simple solution that reacts only to its own states. And it cannot pick any better such local feedback policy. And now to obtain tractability, what one does is one considers the case where we have lots of agents. And this leads one to the basic mean field game model, which is also considered, for example, by Saldi et al. Now, for notational convenience, we shall now define this empirical distribution over agent states as the empirical mean field, GT. And therefore, again, we have this system that we saw earlier here. And what one now assumes is that all the agents follow some shared policy pi. Now, as we let the number of agents essentially go to infinity, we only need to model one representative agent, where the dynamics of this one representative agent is given simply by the same dynamics as before, except that we replace the random empirical mean field by the deterministic mean field mu. and similarly for the objective of the representative agent. And now we can define the mean field analog to Nash equilibria by first defining these two maps. First is this map tilde phi, which essentially maps from a mean field to all optimal policies. So for a fixed mean field, we want to find all the policies that are optimal regardless of which time or state the agent is currently in. And similarly, the map psi, that maps from a policy to its induced mean field if all the agents were following this policy by this evolution equation here. And now the mean field equilibrium, which is the analog to Nash equilibria, is simply defined now as a consistent pair of policies pi and mean field mu, such that the policy is optimal in the mean field and the mean field is generated by this policy. And this has...
May I interrupt for a quick question?
Sure.
Okay, thanks. In the previous slide, I was wondering, the equilibrium that you are looking for, is it mu is a fixed mu, or it's a sequence of mu? It's a sequence of distributions?
Yes, so mu is at each time point, exactly. So it's a sequence of distributions.
Okay, great. And you have a fixed initial distribution that is prescribed, or it can be anything?
Yes, it is a fixed initial distribution. So we start with some mu 0, from which all the states are sampled from each of the agents.
Okay, great. Thank you.
And so this system essentially has nice theoretical properties, as Zaldi et al. Show. So if we assume that the model is continuous, which implies that it is also bounded, since we are really looking at a simple case of finite state and action spaces, then one can show that there always exists such a mean field equilibrium, pi mu, and furthermore, more importantly, the policy tuple that consists of the mean field policy, mean field equilibrium policy, will constitute an approximate epsilon Nash equilibrium in the corresponding finite n-agent systems, where this epsilon, the suboptimality, goes to 0 as the number of agents goes to infinity. So this essentially means that the mean field equilibrium rigorously gives us a good approximate Nash equilibrium in sufficiently large systems. Now what we really want, however, is to compute this mean field equilibrium. And in general, it is unclear how to guarantee that we actually find such a mean field equilibrium. And for instance, what one could do, this is a non-exhaustive list, in certain special cases, of course, one could try to look for analytic solutions. However, perhaps the most widespread two methods are the following two. One is the fixed point iteration, which requires contractivity, which basically tells us we just start with a mean field and then we compute an optimal policy and then again compute a new mean field. And then we repeat this process until it converges. Whereas in fictitious play, we require monotonicity conditions to hold, and we essentially change it up a little bit by using the average policies and mean fields. Yes, I see a question in the audience.
Yeah. Hello, Kate. I have a question about the previous slides. Would you have a bounds on how the error depends on n? The approximation error.
In the paper from Zaldi et al., there were no bounds so far, although typically the mean field bounds are something like 1 over square root n. But this has not been shown in the paper that is listed here.
Got it. Thank you.
And yes, so these are the two methods that are very widespread. However, still they always require these conditions to hold. Otherwise, we are not guaranteed to actually find a solution. And unfortunately, we actually find that these conditions fail very often. And indeed, in our very simple case, where everything is really finite, the contractivity, especially, will fail in almost all non-trivial problems. So what we can show is that if we consider some policy selection function phi, which just selects for every mean field an optimal policy, and assume that this policy selection function has a finite image, which is the case in our case, if we simply put equal mass on all optimal actions, or pick the first optimal action under some arbitrary ordering of the actions, then we find that this fixed point iterator is either a constant, so we really have a trivial problem where the agents can just optimize under any mean field essentially and not care about the other agents, or this operator is not Lipschitz continuous and therefore it's also not contractive. And therefore this contractivity is quite difficult to achieve, and therefore we are trying to look for alternate methods that might be able to still give us a good result. And this is why we are looking into entropy regularized mean field games, which are essentially obtained by changing the control problem to a relative entropy control problem. So what is relative entropy control or reinforcement learning? If we begin with just the conventional optimal control problem, we are just optimizing over all policies the expected sum of rewards. And in relative entropy approaches, what we additionally add to this objective function is this entropy term, which is basically the expected KL divergence under the state distribution between the policy and some prior policy Q. So we put some arbitrary prior policy, for example, the uniform distribution, and we obtain this new objective function, which is not just optimizing all the rewards, but also trying to keep the policy close to the prior policy for a certain temperature eta that controls how close we would like to be to the prior policy. And this really gives us state-of-the-art reinforcement learning algorithms, such as soft actor critic, that also give quite nice provable robustness properties, for example, to misspecifications of the model, so P and R. And so for these kind of relative entropy control problems, we can actually compute the optimal policy, which is actually unique as well. So if we simply fix a mu, a mean field, we have a optimal control problem with the optimal policy given in the following way. The optimal policy puts mass on each action mu that is proportional to the prior policy times some Boltzmann term, where the Boltzmann term has an energy. The energy is here given by this soft action value function, which is almost the usual action value function, which just tells us how good an action is in comparison to take at a specific time t and state x. And yeah, so the soft action value function is essentially computed by using this soft maximum Bellman recursion instead of the conventional Bellman recursion, where really the only thing we do is we replace the typical maximization over all actions in the next state by a soft maximum. So this eta log sum exp 1 over eta part is basically a soft version of the maximum operator over all possible actions u prime. And now, using this unique optimal policy, we can consider the according fixed point operator, where we use these kinds of optimal policies and then again map to the generated mean field. And this kind of fixed point operator has some nice properties. So if we define the relative entropy mean field equilibria as a fixed point of this new operator, then if we assume at least Lipschitz continuity of our model instead of just continuity, then we can obtain the following results. For one, such a fixed point always exists, and that is also true just for continuity. But more importantly, again, the policy tuple of using the mean field equilibrium policy in the n-agent system again constitutes an approximate epsilon Nash equilibrium in the n-agent game, where the epsilon goes to 0 as the number of agents goes to infinity, and additionally the temperature goes to 0. So what this tells us is that at least the suboptimality of that we obtain by using entropy regularized mean field games is at least continuous in the temperature. And finally, the perhaps more important result, we also obtain that this fixed point operator will be contractive for large enough eta. So if we let eta go to infinity, eventually it will be contractive, and therefore we can actually compute this new concept, this new solution concept, eventually. Now, for the proofs, you can find them in their papers, but essentially, as a quick rundown, what it boils down to, let's go back to this slide, is that if we consider the map from any function q to this type of optimal policy, then this is a Lipschitz mapping with a Lipschitz constant that is proportional to 1 over eta. And similarly, if we, or not similarly, but if the q function is a Lipschitz function of the mean field mu as well, then essentially what we have is that this policy selection operator that maps from a mu to the q and then to this optimal policy will be Lipschitz with proportionality to 1 over eta. And therefore, as eta goes to infinity, this becomes arbitrarily small and eventually less than 1. Now, you might ask, obviously, we cannot have eta go to 0 and eta go to infinity at the same time. And that is true. However, in practice, we might be able to find very low eta for which we already converge to a solution, for which we have very little suboptimality gain, since the suboptimality epsilon is continuous in eta in the temperature. And therefore, the hope is that in this way, we can find approximate solutions to mean field games. In particular, we can also argue that since the mean field games are anyways an approximation of the n-agent system, we are losing very little by approximating just a little more to obtain a tractable solution. And so one more difference or one more change we can do is we can notice that the energy-based policy is actually here the key to convergence, and therefore we don't need to bother with this soft action value function. Instead, we can also use the conventional action value function. So if we simply define the policies as proportional to the prior times this Boltzmann term with the action value function from the usual Bellman equation, then we really find that this has the same properties as the relative entropy solution. So therefore, here we have shown that softmax policies, these are essentially softmax policies for the uniform prior policy, they can really help help convergence of algorithms. And indeed, they have often been used before in multi-agent reinforcement learning and mean field games, although oftentimes or usually without formally noting that the regularization is what leads to convergence. Right, so the overall algorithm is given here. So depending on if we use the Q function or soft Q function, we can call it the Boltzmann or relative entropy fixed point iteration. And all we really do is we start with a mean field, and then we compute the Q or soft Q function, the action value function, and define the policy as this softmax policy. And then finally, we compute a new mean field and repeat this process. Now, optionally, if we also want to add onto that the fictitious play, then we can also use essentially the average policy over all past iterations, as well as the average mean field over all past iterations. And this is what we will now evaluate in the experiments. So yeah, in the experiments, we evaluate with respect to the exploitability. So the exploitability, delta J, is defined as a function of policies pi, and it is basically the amount that you can improve your the mean field objective function in the mean field generated by this policy by choosing a different policy than the policy itself. And really, this is the limiting equilibrium quality epsilon of the solution pi in the finite n game as n goes to infinity. And so we consider 4 small problems. The details are not super important here, but you can find them in the paper. So we look at the left-right example, where we really just have 2 actions, and the cost of taking an action is proportional to the number of agents that took the same action. Then we also have the rock, paper, scissors scenario, which is a biased mean field version of a rock, paper, scissors problem. Then we have the SIS problem, which is an epidemics problem where we have basically agents that can take precautions to avoid infections. However, the precautions are also costly, just like the infection period, as well as finally also a small taxi environment where we have a big state space. And now here what you can see is you can, on the x-axis, you can see the temperature, whereas on the y-axis, you can see the exploitability, and to be particular, the mean exploitability over the final 10 iterations of running this algorithm. So, and here as the dashed lines, what we can additionally see is also the maximum and minimum exploitability over the final 10 iterations. So what this means is that if for a given temperature, we have a very high range between these dashed lines, that means that the algorithm did not converge and continued to oscillate. And now what we can see is that as we increase the temperature from 0 upwards, eventually all of these algorithms converge as predicted by the theoretical results. And of course, by adding some temperature, we are no longer able to obtain exactly 0 exploitability, But if we choose the temperature minimally such that we already obtain convergence, then it appears that we tend to get quite good results as compared to without using entropy regularization at all. So the case without entropy regularization is given at eta equals 0. Yes, a question?
Yes, thank you. So I'm wondering, the exploitability that you are showing here, the delta J, is really the exploitability without the extra term in the reward, correct? Or is it the penalized
Yes, exactly.
reward?
It is
Okay.
without. Mhm.
Okay, so if it goes to 0, it means that you really have found a Nash equilibrium for the original, let's say the unregularized mean field game. Is it?
Yes, for the unregularized mean field game, the mean field
Okay,
equilibrium.
perfect. Great, thank you. Yeah.
Yes, and as you can see, the especially in the SIS example, which is shown to the right, which is this epidemics problem, we can see that if we choose an eta of around 0.07 here, then we really obtain better results than otherwise achievable using fictitious play or just the fixed point iteration method. Yes. Another question? Please go ahead.
Yes, just a small question. Thanks a lot for your talk. I'm not sure I understand clearly. The eta is remaining constant during training, or it can also move during training?
Yes, it is constant. So for each of these x points here on the x-axis, we perform the experiment using the specified number of iterations here. So 10,000 iterations of the...
Yes, that's what I had understood. Thanks. Did you try to make it move maybe with training or?
Yes, exactly. So I think in the following so here there's the prior descent method where we try to use the variable temperature, but I guess this is a bit different. So what you're proposing is that you really move the temperature down. Yeah, but this doesn't, the problem is then it starts to oscillate again, right? So because even if we have already converged to a solution, then if I set the eta now to 0, then again, we just start to oscillate, right? Because in the left-right example, for example, we just always choose the side with less people, right? So it always oscillates, regardless of the starting mean field.
Okay, so what you mean is that, yes, even if you change the starting point of the distribution, because you were somehow at a point which is not so bad for a larger eta, you get the oscillation again when you reduce eta.
Exactly.
Thanks a lot.
All right, and so what we can then also do is a reinforcement learning-based solution, which qualitatively gives us the same results. Of course, a bit worse, since the reinforcement learning solution is in itself a bit suboptimal and also random. So, but on the right-hand side, also we can see the result for the taxi environment. And here we really see that by increasing the temperature, it doesn't really improve at all. And so the primary reason we see here is that we really only need randomization in certain states. So this is a kind of limitation, since essentially we solved the reinforcement learning problem 15 times in a row, and this is also quite intractable. And finally, I would also like to quickly point out this prior descent method. So there's this idea of computing a relative entropy solution and then using the solution again as the new prior policy. And essentially the idea is that since we cannot get worse than the prior, then if we find the correct temperature that gives us a better solution, we can iteratively improve our solution while always converging to a solution. And in this case, we can simply use this very simple heuristic. This is just a preliminary work, really, that still shows us, however, that we are able to find better solutions, better exploitability by changing the prior iteratively, even by just scanning over these very simple choices of temperatures. So yeah, to summarize, we have now shown that the contractivity mostly fails even in the simplest settings. And this has really motivated our search for these approximate solutions through entropy regularization. And this entropy regularization and also softmax policies, they provably lead to convergence with a suboptimality that is at least continuous in the temperature. And additionally, we also imagine that the prior policy mechanism is useful for other works. So for example, we have seen works that use this in an inverse reinforcement learning setting for mean field gains. So with this, I would like to now move on to the extension of these types of mean field gains also to dense graphs. And for dense graphs, first of all, why do we even consider dense graphs? The idea is that in conventional mean field games, we have a kind of global interaction where for each agent, they have the same mean field. And sometimes it can make sense to make this interaction local in a specific way, which could be graphical via some graph. And to do this, we can consider limit objects of graphs as the graphs grow increasingly large. And this is exactly what we do here. We use the graphons, which are essentially given as continuous domain versions of adjacency matrices. And so they are really just bounded, symmetric, and measurable functions that are defined on the unit square and map also to the unit interval. And yeah, so for more details, you can see this review of large graph limit theory. But to make the connection to finite graphs, we can look at it this way. So if we look at these step graphons, they are really just like a pixelated version of an adjacency matrix. Right? So if we have, for example, this graph here with 5 nodes, then we say that essentially the interval from 0 to 0.2 corresponds to the first node, from 0.2 to 0.4 corresponds to the second node, and so on. And each element of this matrix essentially has the value 1 or maps to the value 1 always if there is an edge between the corresponding 2 nodes, and to 0 otherwise if there's no edge. And in this way, you can define the step graphons. And for the mean field model, what we will need, therefore, is some description of limiting step graphons. So we need that the step graphons converge to a certain graphon W in a certain sense, as the number of nodes goes to infinity. And to achieve this, a typical definition is the cut norm defined on the space of graphons. So the details maybe are not super important. Most importantly, perhaps, is the fact that the convergence in cut norm is just equivalent to convergence of fractions of occurrences of arbitrary subgraphs in the graph if we randomly pick nodes from the graph. So randomly take a subgraph of the graph. And analytically, this is equivalent to the convergence in a certain operator norm, which will be useful to show all these results of mean field gains later. Now in our experiments, what we will use, and also as an example right now, we will use the following 3 graphons, which is the uniform attachment graph given here, the ranked attachment graphon given here, as well as the P Erdős-Rényi graphon given here. And yeah, so from these graphons, we can then also sample graph sequences of finite graphs that get increasingly big, that can converge in the desired way to the limiting graphon, so in the cut norm, as n goes to infinity, by simply generating graphs in the following way. For each node, we sample its index uniformly from the unit interval, so any random number between 0 and 1. And then, now that every node has an index, we connect nodes randomly with a probability that is simply given by the graphon evaluated at the indices of the nodes. And so now that we have these, the limiting graphon as well as graphon sequences, we can define the dynamics model. And so existing related works focus mostly on continuous time, such as the works given here and a few more as well. So what we introduce here is a discrete time model. So if we define this empirical neighborhood distribution, GTI, as the basically the empirical distribution over agent states that are connected to a specific agent I, then we can simply use this neighborhood distribution instead of the global mean field and insert it into the dynamics P. And similarly, we do the same thing for the objective. And immediately we are done with the n-agent dynamics model. So all we really do is, instead of having this global mean field dependence, we have a local neighborhood distribution dependence. And similarly, we can also do this for example, the infinite horizon discounted formulation. Now, as we let again n go to infinity, the limiting system now is given by uncountably many representative agents, where we have alphas from 0 to 1, from the unit interval, essentially. So since we have now uncountably many agents, representative agents, we also need uncountably many mean fields, as well as uncountably many policies. So we introduce the mean field ensembles and policy ensembles accordingly. And in the limit, as n goes to infinity, these empirical neighborhood distributions, they will simply be substituted by this integral over the slice of the graphon times the mean field at the index of the agent, which is I over n. And yeah, so that means that in the limit that the dynamics of any representative agent alpha will be given as follows. So we simply substitute for the empirical neighborhood distribution we saw earlier here, this integral, as well as for the objective as well. And now we can again define these maps, the set-valued map tilde phi, which maps from mean field ensemble to optimal policy ensemble, where really the policies are optimal for all alpha, as well as the map from a policy ensemble that generates the mean field ensemble, which is a mean field for all of the alphas. And the graphon mean field analog to Nash Equilibria then is again given as a pair pi mu of policy and mean field ensembles that fulfill this fixed point property, so that the policy ensemble is optimal again in the mean field, and the mean field is generated by the policy ensembles. Now, to obtain theoretical properties and guarantees, we must weaken the concept of approximate Nash equilibria very slightly, since under cut norm convergence that we introduced earlier, it is always possible for a finite number of nodes anywhere in the graph to have an arbitrarily different neighborhood that is completely different from what the graphon, the limiting graphon, prescribes. And therefore, we introduce this notion of epsilon p Nash equilibrium, where we have additionally this fraction p now that tells us which fraction of agents does not need to fulfill this approximate optimality, right? So rounded up. And so this informally means if the fraction p is negligible, still it will have a negligible impact on other agents, since we still have this weak interaction property. And therefore, for all other agents that are not in this fraction p, near optimality will hold. Now we give the assumptions. So we assume that the step graphons converge. Yes, a question?
Yes, so, sorry to interrupt. In the previous slide, what you're saying, just to check if I understand, is that it's possible for a finite graph. I mean, it's possible to have a sequence of finite graphs converging towards a graphon as n goes to infinity, but yet each finite graph is not exactly, yeah, it doesn't look exactly like the graphon. Like you can have some neighborhoods that are different from, arbitrarily different, like completely different from what they're supposed to be in the limit, because you are not yet at the limit. And so you want to account for that, and that's why you allow for this p fraction. Is it the way
Yes,
to understand this
exactly.
statement?
Because if we say that they converge in this way,
Hmm.
then this is just almost everywhere
Hmm.
needs to converge, right? So this means that there's always the possibility for a fraction that disappears as n goes to infinity to be arbitrarily different, yeah. So this is a slight weakening of the approximate Nash equilibria.
Okay, great. Yeah, thank you.
Sure. All right, and so the assumptions are that this step graphon sequence converges as assumed in the cut norm as defined earlier. And again, we assume that the model RP is Lipschitz continuous as well as the graphon itself. Although for most results, actually blockwise Lipschitz graphons also suffice for all the results except for existence. Because now what we can show under these assumptions is that under the above assumptions, a graphon mean field equilibrium does exist. And we do this by reducing the graphon mean field game to a normal mean field game, where the states are now slightly different. We simply put the alpha, the index, on the graph into the states. So we extend the state space. And then we can kind of use existence results to prove this. However, for the epsilon p optimality, this is not the case, since we actually deal with finite graphs, and classical mean field games do not really consider graph structures, but instead directly would use the limiting graphon. And therefore we show it again, basically, that for pi, if it is Lipschitz up to finite discontinuities, Lipschitz in alpha particularly, then we find that the finite policy tuple again constitutes epsilon p Nash equilibria, where the epsilon p and p go to 0 as n goes to infinity. And so this might worry one if we have to only consider Lipschitz up to finite discontinuities policies. However, this is not a big deal, since we can also, as done in the following, simply discretize the unit interval and therefore obtain arbitrarily optimal policies that are fulfilling this requirement. So really, we are still able to find such a solution that is an epsilon p Nash equilibrium. So again, we use fixed point iteration, starting at some mean field ensemble, and we apply softmax policies as discussed earlier for convergence if required. And now we propose two methods. One is the discretization approach, where we partition the unit interval into subintervals and take representatives out of each of these subintervals. And then we compute everything only for these representatives. So we compute the optimal policy only at these alpha i's, the representatives, and also recursively compute a mean field approximation of the mean field ensemble recursively also at each of the alpha i's. And we can really show that this is provably exact as the partitions become arbitrarily fine. And the second solution is the direct reinforcement learning solution, where we just consider the graphon mean field game as a normal mean field game with extended state space that is considering the alpha as part of the state. Now we consider two problems on the three graphons we mentioned earlier, which is again the SIS graphon problem, which is adapted from the epidemics problem from before, as well as the investment graphon problem, where we have lots of firms that can invest in product quality and obtain profits proportional to their quality and decreasing with the neighborhood quality. So it is kind of the case that the graph models overlap in product functionality, for example. And as we can see here for the SIS graphon problem, the results are quite convincing. Here we have regularized a little bit to obtain convergence. So we can see that, for example, for alpha equal 1, which is essentially no connectivity at all, so no edges at all, we have that nobody takes precautions if their alpha is equal to 0, since they really can't get infected anyways. Whereas for the others, they move into an equilibrium, and then at the end, since the game ends at t equal 50, nobody will care about infections anymore. And similarly for the other examples. And we can do the same thing for the investment graphon case, where we do not need regularization, as it already converges. Here, the deterministic threshold policy will essentially let agents invest up to a certain quality, and after that, they do not allow more investment. Yes, and finally, we can see that the PPO solution on the bottom is qualitatively quite similar to the discretization approach seen here. So we see that the second method using direct reinforcement learning is agreeing with the solution using discretization. All right, so that is it for my talk. Thank you for your attention. You can find more details in the papers. To reiterate, we have formulated simple approximate solution algorithms for mean field games, as well as graph-based mean field games. Now, where can we go from here? Well, there's a variety of interesting topics, such as the direct application to actual finite end systems, as well as further investigation into prior iteration, more general settings, as well as a number of other extensions that what one could think of. All right, thank you. Now, if there are any questions, I will be glad to answer them.
Thank you very much. It was a very nice talk. I think it was very clear. I have potentially a few questions, but maybe, I don't know, if someone from the audience, if there are questions. Okay, otherwise I can start with one maybe. So in the first part of the talk, on the taxi example, you mentioned that, if I remember correctly, sometimes you need to randomize, I mean, the actions at equilibrium, the actions need to be randomized in some states. So I imagine that, I understand that in this case, taking a softmax policy maybe is not the best thing to do, because then you are like randomizing for any state, randomizing actions for any state. I was wondering if maybe fictitious play or this kind of methods could help, because you might, so without, let's say, softmax, or maybe with a small softmax with a small temperature, then maybe over iterations you might accumulate randomization, and then when you average, you end up with. Do you think this could work? Have you tried, or?
Yes, this could certainly work. We have not tried this for the reason that essentially this is quite expensive to do, since we train a queue network, a deep queue network, and then to take the average over all past queue networks would mean, or all past policies would mean that we have to keep all the networks at the same time. And then
I see. Yeah.
This is
right. So this is an example where you have a huge number of states, right? Like 2 to the 20 something.
Exactly.
Okay, makes sense. Thank you. Yeah, I see the difficulty. And another question was, so you mentioned the shortcoming, that you were motivated by the shortcoming related to the strict contractivity that often fails.
Yes.
Do you think that the monotonicity condition is satisfied in your examples, or do you know if it fails as well?
So in the monotonicity condition essentially says that we want to kind of get away from states that have already lots of other agents in it. But this is not the case, for example, in the SIS example, since we always want to not be infected, regardless of how many people are currently not infected. Right? So this is an example where the monotonicity condition really fails. And this is also the reason why fictitious play doesn't really converge to a good solution here.
I see. Yes, I guess it depends on the cost function, etc. But I imagine it could fail in this case. Yeah, there is no natural monotonicity. Okay, thank you very much. Are there more questions? Okay, otherwise we are right on time. I have maybe other questions, but I guess I can reach out later, maybe.
Sure.
Okay.
Thank you for your questions.
Yeah, well, thank you very much to you for your talk. It was very clear, very nice. So this was the last talk of this year, but we are going to continue in 2022. So we will keep everyone updated. And yes, well, thank you everyone, and thank you again, Kai, for your nice talk.